I'd like to start today with some homework correction. I've got all of the different sections laid out on the smartboard here. I was wondering if there was any particular questions that you would like me to do in each section. If not, I'll probably just pick one or two to do just so you can see a few more. So looking at the questions in section number 1 here, is there any letter in particular that you would like me to do, chat? So not seeing any suggestions, I'm going to pick, let's do A, because A has a lot of the secondary trig ratios in there. I think these were mostly warm-up questions anyway. From what I can tell, they're relatively simple. And I am going to admit that I have not done the answer key to this homework yet, so I'm going cold. So if I make any mistakes, I apologize in advance. So cotangent x. So I'm not going to rewrite that expression, but I am going to start converting them to the primary trig ratios. So cotangent is tangent's primary trig ratio. So it is cosine over sine, which is 1 over tan. Secant is cosine's primary trig ratio. So that's 1 over cos. Oh, not sure what happened to my pen there. And then that's the left side. And we want to do the right side of that as well. So cosecant is sine's primary or secondary trig ratio. So that's 1 over sine. And, well, as you can see very simply, that cancels out with that. So we're left with 1 over sine x, which equals that side. So I'm hoping with these warm-up questions that you were starting to get at least comfortable with the idea of this left side, right side check thing. These are not solving equations. We're actually going to be seeing that later today. But they're good warm-up questions just to get used to especially the secondary trig ratios and all of their reciprocal functions. Okay, so let's take a look at number 2 here. Is there any particular letter in number 2 that you would like me to do? I hope I'm not waiting too long. I have to wait a little bit because I know there's a little bit of delay. But I'm not seeing any chat suggestions. So let's take a look at, let's do D. Let's do one of the fraction ones. So I again going to start right away converting this into its proper format. So we have normal tans here, but we can't work with tan either. We need to convert those to sines and coses as well. And we know that tan theta is equal to sine theta over cos theta. So we're going to have 1 minus sine theta over cos theta all over 1 minus cotangent theta, which is cos theta over sine theta. And that's the left side. And our right side is minus tan theta, which I could just leave as minus tan theta, but we'll write it in its, I guess, expanded form of sine and cos, sine over cos. Okay? So now I've got to get this side equal to that side. The right side is the simpler side, so I'm going to work on the more complex side. And what I'm going to do is I'm going to find common denominators for both the top and the bottom. So I'm going to multiply the 1 here times cosine theta, top and bottom. And I'm going to multiply the 1 here by sine theta, top and bottom. So that's going to give me cos theta minus sine theta at the top, divided by cos theta, which is going to be the common denominator now. And that's all divided by sine theta minus cos theta all over sine theta. And now this is a division of a fraction. So that means multiply by the reciprocal. Oh, I forgot the theta beside the cosine here. So cos theta minus sine theta divided by cos theta times the reciprocal of this guy. So sine theta over sine theta minus cos theta. And this is all coming together nicely. So we have the sine over cos right here, which is what we're looking for to get to our tangent, right? Sine over cos. But these two numerators and denominators here and here look similar, but they're not the same, so I can't cancel them out. But the only thing that's wrong with them is that the signs are backwards. So if I factor out a -1 from that top statement, it's going to become negative cos plus sine, which I can then write as positive sine minus cos. And that is now the same as this bottom one, which I'm actually just going to write underneath here, since I know what's happening. And I'm going to group the sine theta and cos theta together, because you can do that when everything's multiplying and dividing, right? You can move the numerators around, you can move the denominators around. And that now cancels out with that, because they're exactly the same and everything's multiplying. And we're left with negative sine theta over cos theta, which is the same thing as this guy. So that's done as well. So good example here of how comfortable you need to be with your fraction rules. Unfortunately, there's no room for any doubt anymore. You have to know how to add and subtract fractions, and you have to know how to multiply and divide fractions, because they're going to be mixed together with other types of expressions. Let me know if there's any questions, folks. I am going to move on here. So this was question number 3. These were just getting more and more complicated. I think I wouldn't mind doing the first one. Yeah, let's do the first one and see what happens. So both sides look rather complicated, but the first side is the only one where we have values that aren't in sine and cosine format. So I'm just gonna, because I don't have enough room here to do the right side, I'm just gonna do the left side for now, and if I need the right side, I'll go and do it in a minute. So let's rewrite everything so that it's in the proper format with our sine x and cos x Lego blocks. Tan is sine x over cos x. Secant has cosine, 1 over cosine, my mistake, as its reciprocal function. So, I guess we're already where we need to be, because we've got sine squared x here when I group those two together, and everything's over cosine x as a common denominator. So that one actually wasn't as hard as it looked. And to tell you the truth, I think all of these folks are basically the exact same scenario as the one we just did here with D. Very, very similar to D, except both sides are fractional. So if you don't mind, if there's no questions, I'm going to skip doing those, because it basically be the same kind of structure. So I'll give you a few seconds to let me know if you want me to do B, C, or D in number 3. Okay, so I'm not seeing any questions coming up, so I'll move on to number 4. Is there one in number 4 that would have been a little bit more challenging than others? I believe D is very, very similar to the one we did in class, if not the exact same. Normally that would have been one that I would have tried with you, because it seems a lot more complicated. Are there any letters you'd like me to do in 4, folks? let's do C. Sine x plus cos x. Now I'm going to immediately write cotangent x as cos x over sine x. And that's all divided by cotangent x, which is also cos x over sine x. And the other side is secant x, which is 1 over cosine x. Not sure if some of you are starting to gain my hate for the reciprocal secondary trig functions. Okay, let's see what happens here. I'm just double checking, making sure I wrote everything correctly. So at the top, it looks like we're going to need a common denominator. So the sine x here is the denominator. I need a sine x under this denominator, so I'm going to multiply the top and the bottom by sine x. Now, again, and another thing I'm not sure of, I can already see where this is heading. My brain is now like 3 steps ahead, and I know that there's going to be a sine squared x, cos squared x coming up. And I wonder how many of you are starting to gain that ability to see ahead now that you've done a few of them, because that really helps you to be able to do the work efficiently. So we're going to have sine squared x plus cos squared x all over sine x. And that's all over cosine x sine x. So I hope you were able to follow along with that. Move my equal sign to the right spot. And now we're going to change the sine squared x plus cos squared x to 1. And I'm also at the same time going to rewrite this division as a multiplication by the reciprocal. So we're going to have 1 over sine x times sine x over cos x. And the sine x's cancel out at that point. So we're left with 1 over cosine x. Gosh, I enjoy doing this. I don't know why, but this is so much fun. So weird. It's so satisfying when you get to that end result and they're the exact same on both sides. Anyway, I digress. Are there any other ones from this section that you would like me to do? All right, let's move on then. So this is the new stuff for today. The last section of trigonometry. Trigonometry is an enormous unit in the grade 11U course. So many different sections. We started with reviewing sine, cos, and tan in triangles, sine law, cosine law. Then we jumped into the angles and standard position. Then we did identities. And now we're going to be doing solving trig equations. So it's a pretty massive unit. Cool stuff though. So let's solve this. Now we are asking you to solve for theta. This is an equation. This is no longer an identity. We might still use identities, but this is solving an equation. So we want to get theta all by itself. So how would we go about doing that? Well, treat it like a regular algebra scenario. We're going to move the -1 over to the other side. I'm going to do it in multiple steps just so you see exactly what's going on. And then I've got to get the root 2 out of there. Well, that's multiplying on the left, so it's going to come and divide on the right. And this should look very, very familiar. We're starting off with an actually relatively easy one here. This is basically going back to what I was getting you to do in the angles and standard position section, even in your assignment that you had in that section. How do you solve for theta? Well, you're actually going to have 2 different answers based on the magic circle here. Where is sine positive? And the reason we have to consider the magic circle is because of the domain that they gave us in the question. If I'm going from 0 to 360, I've got to consider every possible answer where sine theta is equal to a positive value. And we know that that's in the first and second quadrant. Now, 1 over root 2 is not technically in the right format. That should be rationalized. So you may not be recognizing it yet. I'm hoping you do, though. But this is root 2 over 2. And when sine theta is equal to root 2 over 2, there's a very special angle that happens at, and I'm hoping that you all remember what angle that is. That's at 45 degrees, or pi over 2. No, pi over 4, sorry. Okay? So we could either answer this question in degrees or in rads. Now, because this was given in degrees, we technically should be using degrees. Okay, but I just wanted to kind of throw in a rad measurement there to remind you of your rad measurements. So 45 degrees is one of the answers. But because the sine is also positive in the second quadrant, what is the mirrored angle over here? And my picture is completely off scale here, but you get the idea. What's the mirrored angle over here from 45? Well, that's 180 minus 45. 180 minus 45 is 135. So those are your two solutions to that trig equation. Now these get a little bit more complicated as we go on. That one was a relatively easy one. I'm just going to pause for a second here. Are there any questions about that solving scenario? Not seeing any questions. Let's move on to the second one. What I would like for those of you that are able, can you do a variable substitution in your brain and see that this is 3x equals x plus 1? And if you can see that this is 3x equals x plus 1, then that is just a regular algebra question right now. We have x's, or cosine theta, on both sides of the equation. And in algebra, when you have x's on both sides of the equation, you have to get them all to the same side. So let me just write what I'm talking about here, just so you can see it. I wanted you to try to mentally do it, because if you can mentally do it, you don't have to write it down. But I could replace cos theta by x. So what would you do in an algebraic scenario in this case? Well, you would bring the x over to this side. And that's what we're going to do. We're going to bring the cosine over to this side. And I'm going to show all the steps. If I bring the cosine theta over to that side, and I want to do a quick little aside here for a second. There's a huge difference between that statement and this statement, okay? Could I combine those two, cos 3x minus cos x? And if you can, why? And if you can't, why? Could I combine cos 3x minus cos x? What do you think, chat? Can you all still hear me out there? Chat? Hello? I don't want to continue until I'm sure you can still hear me. Okay, so you can still hear me. Okay, maybe there's just a lot more lag today than I'm used to. All right, yeah. So yeah, we can't, there's no way you can combine cos 3x minus cos x, because the 3 here is trapped inside of the cosine, which means these are not the same type of term. They're not like terms. But these are like terms. I've got 3 of these things minus 1 of those things. Those are like terms. So these can't be combined. But these can. So we've got 3 of them minus 1 of them. That means we have 2 of them. Isolating for cosine theta gives us 1/2. And again, I'm hoping that you'll recognize that as being one of the special angles from our magic circle. Now, what 2 quadrants are cosine theta positive in? So remember that cosine theta always goes with the x value. You can use the Astica rule if you want, but I always think of cosine being attached to x. So x is positive in these 2 quadrants. Correct, chat. So now which special angle is cosine theta, specifically theta, going to be if cosine theta is equal to 1/2? So do your 1, 2, 3 trick. Cosine theta is the first column. 1/2 would be this number. What angle is that? So I'm hoping very quickly you can see that that angle would be 60 degrees. So what would be the corresponding angle in the 4th quadrant? Well, if this is 60, 360 minus that number will bring me back to this one. So correct, it would be 300 degrees. And that's how you solve that one. So those 2 were warm-up questions. Let's take a look at this one. So one thing I want you to notice is now the domain is written in rads. So we're going to be wanting the answer in radians. This one's a little bit tricky. I would like you to do a variable substitution again, but do you have trouble doing variable substitutions when the variable you're substituting is already an x? So think of a capital X to replace what's going on here. What kind of equation is this? If I write this as a capital X, wouldn't this become 2x squared? And that, ladies and gentlemen, is a quadratic with trigonometry hiding inside of it. So I would actually do the variable substitution here just to help me see that quadratic equation. I would do the product and sum tree. You can do whatever method you like to factor this. So that would be 2x and x, and it would be 2 times minus 1 and 1 times 1. So this one's pretty easy to even factor. That would mean that 2x plus 1 equals 0, or x minus 1 equals 0. So if we treat this as a quadratic, we can do the quadratic part. But we're not done, because we have to now resubstitute. These are capital X's, sorry. We have to resubstitute that x is equal to cosine x, little x. So we'd have 2 times cosine little x plus 1 equals 0. And cosine, excuse me, little x minus 1 equals 0. And then we'd have to isolate in both cases. So you would end up with cosine x, equals negative 1/2. And cosine x equals 1 as your 2 possibilities. That means we're going to have 2 answers here. And are we going to have 2 answers here? Potentially we could have 2 answers there. I'm going to have to think about that one. Yeah, yes, we're going to have 2 answers here too. So you're going to have 4 different answers for little x here. So if we look at the first one, where is the cosine negative? The cosine is x values. X values are negative. Oops, sorry. Going too fast. Cosine values are negative in this quadrant and this quadrant. Now, what is the related acute angle? Well, we actually did one recently for cosine is equal to 1/2. That's 60 degrees. That's the related acute angle. But we're over here. So it's not 60. It's going to be 180 minus 60, which is 120 degrees, right? Well, if this is 60, that means this is 60. We know that the flat line is 180. 180 plus 60 will give me my next one, which is 240. So those are the two angles. Now we have to write those in rads. All right. So do you remember how to convert to rads? Now you could have written these out in rads in the magic circle if you wanted to, but a lot of people I know will actually solve it in degrees first and then write it in rads. So I don't know if you remember the conversion factor for rads. You multiply by pi over 180. So that'll be, both of them are divisible by 6, right? So it'd be 2 pi over 3 for this one. And this one will be 4 pi over 6 is what I'm getting if I divide by 60, but that'd be, no, wait a second. Am I messing up here? I might be going too quickly. Divided by 60 is 2. Divided by 60 is 3. Divided by 60 is 4. Divided by 60 is, okay, sorry. Yeah, I did mess up there. So those are your two rad values, if I didn't mess up. Now for cosine x equals 1, what special angle does cosine, does theta have to be, or x have to be, sorry, so that I get 1 as my answer? Well, this coordinate right here is 1, 0, because this is a radius 1 circle, right? That would be 0 degrees. But there's another one. Because my domain goes from 0 to 2 pi, including 2 pi, 2 pi is my other answer. So we're getting 4 different answers for that question. And that's how that works. Let's look at one more. Before I do that, let's just recap this one because it was a pretty complicated one. So if you see an equation that kind of looks quadratic because of a power of 2, try a variable substitution to see if it is. And the variable we substituted, we said that big X is equal to cosine little x, okay? So we replaced all of our little x terms, or yeah, terms by big X's, okay? Factored it as a quadratic, found what the solutions would be quadratically, and then resubstituted in the cosine little x. And then we started doing the trigonometry solutions. So our answers are 0, 2 pi over 3, 4 pi over 3, and 2 pi. And just to take a second to realize how far you've come if you understand even just this part. So that's some pretty big headway that you've made. Okay. Moving on to, I believe this is the last one. Just going to double check here. Yeah, that's the last question. Solve 6 cosine squared x minus sine x minus 5 equals 0 for 0 to 360. Round approximate solutions to the nearest tenth of a degree. What is the problem here? At first glance, you might say, hey, this is a quadratic just like the previous one. But unfortunately, it is not, because this is a cosine and this is a sine. I can't do a variable substitution right now because I would just get an x and a y, which is not going to help. So there's something else we need to do to fix this before we start. Does anybody know what? I'll give you a hint. We need to get everything written in the same trig ratio. Is there any way that we could get everything written as sine x or sine squared x, perhaps? Do you see something that we could change? I'll give you another hint. It's based on an identity. What is the identity for cos squared x? And I know it's a little bit hard to type. Anybody remember the identity for cos squared x? That's right. It's 1 minus sine squared x. Now, why am I thinking that? Because if I change this to 1 minus sine squared x, now I only have sines involved. So let's look at what it would look like. If I replace cos squared x by 1 minus sine squared x, I get 6 times 1 minus sine squared x minus sine x minus 5 equals 0. Expanding gives me this. Simplifying gives me this. 6 plus negative 5 is plus 1, right? And I'll give you a second to make sure you understood everything I just did. So we took this cos squared x and we replaced it by 1 minus sine squared x, because that's an identity that we used. Why did we do that? Because I can't work with coses and sines in an equation. This is not even an identity. This is an equation. Whoa, I'm losing my voice. I got no water around. Let's see if it comes back. Yeah, so you can't work with a cos x and a sine x in an equation like this. So you use the identity to write everything as sine x squared and sine x. And then you try to write it as a quadratic. Now, I don't want to have a negative 6 in front of this quadratic. I can't factor out a 6, but can I factor out a negative 1? We can do that. So this is now a quadratic. And just to prove to you it is, I'll do a variable substitution. Let's set big X equal to sine x. And we can write that as a quadratic now. And I am not going to finish this one off because it's technically in your textbook. So you can go look at the answer yourself. I'll just write the page number here so you can go find it. It's chapter 5, page 406. So you can go take a look at the rest of the solution, or you could, what I would suggest you do is you try to solve it on your own. See if you can come up with the correct answers. Make sure you're following the correct domain. All right, the domain is 0 to 360, so you may end up with 4 more answers again. Be very wary. I haven't actually looked at the solution myself, but they do say to round approximate solutions to the nearest tenth of a degree. That's making me wonder if you're actually not going to even get some of the special angles this time, which can happen, right? 30, 45, 60 are our special angles and all of their counterparts in the other 4 quadrants. But what if you got like 32 degrees? Well, there still is 2 answers, but they're just not going to be very nice decimal values in cases like that. So I'm not sure what's going to happen. Try to answer it. Go look at the answer in the book, and that's going to be it for today's lesson. You will be getting some homework questions from the book to practice. I've shown you as much as I can. There may be some challenging ones, but they're basically going to be similar to this. So I'm going to stop recording here for the sake of YouTube.